Okay, everybody ready? Okay, please have a seat. Right, let's move on. So Chris is going to talk to us about quantum trajectories. Thank you, Chris.
Yes, so this is a talk which comes from another direction, really. It's the talk which is based in quantum theory, and in particular, David Bohm's approach to that, and of course, Louis de Broglie's approach to that from beforehand. So, as I've said earlier, when I introduced myself, I worked with Bohm and Basil back in the 70s, and we created some visualizations to try and understand how David Bohm and Louis de Broglie's theory work. I mean, I do normally refer to it as the de Broglie-Bohm theory. It has become fashionably known as Bohmian mechanics, which is not a great name for it, and one which David Bohm himself would not have liked, I think. And I think that one should give due credit to Louis de Broglie. After all, he virtually got the Nobel Prize for his pilot wave theory. Certainly when he developed his ideas, he was thinking very much along the lines of the pilot wave, which you can see if you read his Nobel lecture.
Should be the middle one. I know that.
Oh, there we go.
Yeah.
So, anyway, so much is history. When was it? 1927, when Bohr and Einstein were debating some of these issues, and incidentally, of course, Louis de Broglie was also at the 1927 Solvay Conference, and it's often said that he was defeated at this conference with his ideas on his pilot wave. When in fact, if you go into it in some detail, which is a very nice book by Guido Bachier-Lupi and Anthony Valentini, which just does that. It's called Physics at the Crossroads. He shows that in fact there were no sort of knockdown arguments against Louis de Broglie in 1927. In fact, it was much more, I think, to do with personalities. So anyway, there's obviously a big revolution at that time, which led Bohr to say that actually there is no quantum world. We had a classical world, but there is no quantum world. There's only an abstract quantum physical description. We have the Copenhagen interpretation, in which probability is inherent and fundamental. But even from 1927, there was an alternative. And you could speculate how physics might have developed had Louis de Broglie been a little more forceful at the 27 Solvay Conference, and people had taken on his ideas, so that instead of throwing out everything to do with the classical world, namely trajectories, particle trajectories, if they had been retained at that time, how might we be thinking today? If someone came along and said that, after 100 years of calculating particle trajectories, God forbid, someone came along and said, no, those don't exist. We would think they're totally crazy. So I'll probably take the middle one first. This one. Yeah, so there's not many equations in my talk, it's mostly pictures, but just to say that what was available back then was this alternative interpretation of the Schrödinger equation, in which you could reformulate it. There are sort of two approaches to this. On the left-hand side here, we have the second-order version, which is the version of the theory which David Bohm published in 1952 in his physical review papers. And essentially, one makes a substitution in the Schrödinger equation, separates the real and the imaginary parts of the equation, and you end up with an equation which looks very like the Hamilton-Jacobi equation, and another equation which looks like a continuity equation. But this extra term here appears, which isn't in the classical equation, and that has this strange form here. It's an additional potential which operates on particles. and in fact there's modifies the Newton law in this way. So we have a quantum potential which gives rise to a quantum force. The momentum of the particle is given by the gradient of the phase of the wave function. Now this is just quantum mechanics really, okay? We haven't done anything, we just made a substitution and rewritten the equations and said, right now, how can we interpret these? And so you can say, well, this is the momentum of the particle. We can integrate this equation, and then we can calculate particle trajectories. Now, there's a whole alternative school of Broglie-Bohm supporters who say, no, we don't really want all this extra Newtonian stuff, this thing which is couched in terms of accelerations. Much better just to say that theory is just this, and this actually is the same as this down here, which is that it's a first order theory, first order in the sense that it's only the first derivative there, and we interpret this on this side not in terms of forces and accelerations, but we say this equation defines a force, but this force determines a velocity, okay, not an acceleration. So this is an Aristotelian force, which produces the velocity and the inertial state. The state when there's no force is simply rest. And as always in situations where there are conflicting groups, things get quite heated between the second order and the first order people. However, from my point of view, I think they're both actually equivalent. There's no good reason why one has to take one rather than the other. So what then happens if we do some calculations with this? Well, the first one I did, and actually thinking of Basel, I remember very much just over here in Birkbeck one day after we had done the two slit calculations, he asked me, had I ever seen these film loops, which were produced by Goldberg, Shea and Schwartz, showing the probability density as a particle tunnels through a barrier. And he said, have a look at these, Chris. Do you think you could do a quantum potential version of that? I said, okay, I'll have a try. And this is a modern version. Initially, that was just a 16mm movie, but here we've got a modern version, whereby the red outline there is the classical potential. Particles are coming into the classical potential, but what they actually respond to is this quantum potential, this Q plus V, which is the blue shape there. And these initial particles coming in, the way I've set this up, all have an energy less than the barrier height, so there shouldn't, classically, they would all be reflected. But quantum mechanically, they, if we follow through Bohm's approach, you see this quantum potential lowers the barrier and allows the particles through. So we can have a picture of quantum tunneling, right, which is much closer to the classical view. Okay, namely, the particle can get through the barrier because the barrier is not so high, because the quantum potential has reduced it. Yeah, so yeah, you can see that again. Going back to the 1927 conference, Einstein also proposed there a problem which he thought really sort of exposed one of the problems with quantum mechanics. And this was before, of course, the Einstein-Podolsky-Rosen experiments and many others. So this was a very simple experiment where you have a beam of light or particles, it could be, which impinge on a slit one at a time. Beyond the slit, it's this bank of detectors. And the problem that Einstein saw with this was that when you ran the experiment, one particle at a time, only one of the detectors actually would receive the particle. And so the problem for Einstein was, well, why is only one detector receive? Why does a particular detector receive the particle? And the answer from the Bohrians, oops, let's go that way, was, well, that's just random. Okay? You can work out the probability that a detector will fire, but which one actually fires is random. And Einstein saw in this also a non-locality, because apart from the thing being incomplete and you couldn't explain this, there was also a non-locality. So, well, if that detector fires, how come all the others know not to fire? So there's a non-locality in this as well. And so, there was a clear explanation for this, which is that if you take the de Broglie approach of the pilot wave, and as the slit narrows, the wave spreads out, the particles follow the rays of this wave, and since there's a definite particle with a definite trajectory, it's going to hit one of the detectors. So we know that there's a definite outcome in quantum mechanics because you started off with a definite position for the particle. So a definite initial condition leads to a definite final position. So there's no need for randomness. There's no need for any non-locality. But there's a caveat here, which is I think often when people think about quantum mechanics, and if they've done the first course in quantum mechanics, well, in the old days anyway, I don't think it's like that now. In the old days, everything is done in one dimension with a single particle. But this is actually very misleading, and I think it leads to a misinterpretation also of quantum theory in general and the Broglie-Bohm theory in particular. I wanted to show how this is the case by simplifying it. Okay, it doesn't look like it's been simplified, but it has. There's only two detectors now, and I'm going to consider these two blue arrows as representing waves, two waves which go to either one detector or the other. So there's a psi left and a psi right. And the detectors have wave functions phi left ground state, phi left excited state. And what that is, you can think of this as a one-dimensional system which moves along its axis so that it's non-overlapping. Okay, so this is when the detector moves, it's a definite outcome. And similarly for the other one. And now to actually describe this quantum situation, we're no longer talking about a particle going along in real space. We now have to consider this as the wave function of the system, which is obviously not in everyday space. It's a function of x, the particle coordinate, y1, the detector 1 coordinate, y2, the detector 2 coordinate. And that's the space in which the wave function evolves. And if you work out then in Bohm theory what happens, first of all, we have to now talk in configuration space. And we find that how this looks in configuration space. And I'm a great fan of being able to visualize things. And so if you make things in 3 dimensions, okay, you can see them. When you go to 4 dimensions and more, it's all a bit more complicated and non-intuitive. So here, this packet in the middle is how we start off, okay, with the particle in the slit and these 2 detectors just sitting there in their ground states. And that's represented by this blob in the configuration space here. As the particles go towards the detectors and the detectors move, this initial wave function splits into these 2. Okay, now if you take away the number 1 and number 2 trajectories, that is what quantum mechanics would tell you. And it will tell you there's a probability that detector 2 fires while detector 1 remains in its ground state and vice versa. And which one actually happens, you would just have to say, okay, randomly. But if you put in the initial positions of the particle in the slit and the particles representing the detectors, then you get definite trajectories. Okay, and so you get a definite outcome for this experiment. Namely, if it were to be the case that the particle started here on the right-hand side of the slit, then the right-hand detector's going to be the one that ends up firing. And if it started on the left-hand side, then the left-hand detector's going to be the one that ends up firing. And we can say that we don't, as a definite outcome, because there's a definite initial condition, and there's no collapse of the wave function here. Okay, there's no need to collapse the wave function in this case. And I'll show you some more examples of this as we go on. So I started to write down what would we learn from all this. Well, the first lesson I think we can learn from that it is possible, contra Bohr, to conceive of a definite and deterministic quantum world, and a mode of description which fulfills to a higher degree our accustomed demands regarding the vectorial relationship between cause and effect, quote from Bohr, which he said it's not possible to do that. The true arena, which we have to understand, in which quantum mechanics plays out in the Schrödinger theory, is configuration space, and that's irreducible. Okay, you cannot formulate it in real space. There's no wave packet collapse, only separate channels in the configuration space, which may, if things go right, become decoherent. In de Broglie-Bohm theory, the system has to be in one of those channels. Ultimately, we have to describe the configuration space wave function of the whole universe and calculate that. But luckily, we don't have to, because everything factors and we can isolate systems to discuss that. But this is a wholeness which really is in the theory. So I also tried to think about how some of these things could be similar, or at least analogous, or have some kind of parallel with what goes on in the DU theory. And the first obvious thing is that there's an absolute objective reality, okay, just as there is in the DU theory. And this is opposed to the probabilistic and observer dependent nature of standard quantum mechanics. And just as in DU theory, quantum mechanics would be seen as a statistical description of a deeper deterministic process. Both DU and WB have explicit non-locality, and neither of our two theories which we're considering require collapse. So let's have a look at measurement, and I think here there's a bit of a divergence in the approaches of the two theories. So we can just think of a very simple example. Let's think of that particle going through the slit, and here we have the slit at the bottom, and this is time going up pace, or you can think of this just as distance from the slit. So if you just let that wave packet evolve, then this is effectively a momentum measurement, okay? Because then by calculating how far along the x-axis the particle has gone in a given time, you could work out its velocity and hence its momentum. It's interesting when you do this, you see that the initial momentum in the packet in the x direction, okay, the initial x component of momentum, which is all we're considering here, is actually 0. But in the far field, the values of the momentum are actually the momentum eigenvalues. So this is effectively a momentum measurement, and we see that in Bohm's theory, the values which are associated with observables are not the eigenvalues necessarily, unless you measure them, in which case they become the eigenvalues. Here's another example, which I will just show because I like it. But, yeah, so when Bohm was ejected from the States and he went to work in Brazil, he worked with Schiller and Tiomno, and he produced a theory, Bohm-Schiller-Tiomno theory of spin. And one of the calculations that I carried out, again, in the 80s now, was to look at what happens when you do a spin measurement. So here, just to explain quickly, the particle comes in with its spin in the x direction, just pointing along here. The little arrows here are showing the inhomogeneous magnetic field. And if you calculate the trajectory according to the BST theory, and you calculate the spin direction, you see that as the particle progresses through the magnetic field. It processes, but that as time goes on, the trajectories separate within the field, and the spin direction either aligns with the field or against the field. So we're measuring sigma z here, and when it starts off, it's not in an eigenstate of sigma z, okay? It's just as in sigma x. But as the measurement proceeds, we see that the spin direction actually evolves along the trajectory until it becomes one of the eigenvalues. So the key point here is that measurements in the Broglie-Bohm theory don't just reveal what was there in the first place. So measurements, in a sense, are not faithful, like they are in classical theory. Okay, when you measure something, you assume that's what was there. Whereas in quantum theory, it's never possible to say that. It's a definite stretch of the imagination, even in the Copenhagen theory, to suggest that the result of your measurement is what was there in the first place. So certainly, we see very clearly from the quantum trajectories that measurements are not faithful. They don't just show you what's there.
How does the equation for the spin look like?
Yeah, when I made this talk, I said someone's going to ask me how does that look. So could I show you later? Yeah, otherwise,
quick question.
Well,
would it be so that the position measuring, when we're measuring position, you're actually revealing pre-existing values?
Oh, apart from, yes, you're right. If you measure places, then that is the only case in which you would be revealing what was there, because position plays a special role in this theory.
And also, would that also apply to momentum if you switched to a momentum basis?
If you formulated the theory in momentum space, I guess yes, but there's hardly anyone's done that. I think there is one paper on that, but yeah, you want to have the symmetry there, I guess. Yeah. Okay, so that's as I called it, lesson 2. And I thought, in relation to DU theory, I don't know if this is correct or not, but it appears to me that measurements in DU would be just like classical measurements and would simply reveal the definite actual state of affairs. And I thought if the dynamic universe wanted to be more like quantum mechanics, perhaps it could somehow, I have no idea how, take on board this idea that measurements don't actually necessarily reveal. Okay, so I forgot this had a music soundtrack, but this was something that I made with an animator from Romania. In fact, it was made for this film about David Bohm, which has a website here, internetpotential.com, and this is obviously the 2 slits. And when I first did those 2 slit calculations back in 1979, I had this image in my mind of this simulation, but it wasn't until almost 40 years later that I found someone who was able to operate this animation software to produce this. So what you see there is the grey is the quantum potential. Obviously, the lines are the trajectories. And if you want to find out more about David Bohm, you can always go to watch the Infinite Potential movie. So, lesson 3, quantum interference is consistent with particle trajectories, which of course was not thought to be the case. You can't have interference and particle trajectories. You can't have a particle going through one slit and see interference, whereas because of the guiding wave, or if you like, because of the quantum potential, you can, because that's formed by the wave going through those slits. And there's a sense then in which the wave function at a point, or the quantum potential at a point, is actually encoding information from the whole of the relevant environment. So this is a bit like DU as well, where the local point has information about the whole universe in principle. Yeah, so the potential energy at a given point is determined by global constraints. So both du and dV treat particles as having well-defined locations. The wave-particle duality is interpreted as an outcome of the whole system, the whole evolution of this configuration space wave functions, not an inherent feature of particles. In the dynamic universe, interference arises out of global energy constraints. In the de Broglie-Bohm theory, interference arises from the quantum potential or from the Aristotelian law of velocities, which reflects energy arising from the global setup. Okay, so Feynman once said, well, the closest he came to ever saying anything about hidden variable theories was that it would be absolutely impossible to cook up a hidden variable theory which could account for the loss of interference when you measure through which slit the particle goes. But he wasn't thinking in terms of configuration space. So we can have a look at that. So there's another of the animations from that movie. So there's a little detector sitting just in between the slits, and that's measuring through which slit the particle's going. And you can see the effect is to take away the interference from the trajectories. There's no wiggles in the trajectories anymore, it's just these straight lines. So I should explain how this happens, because this detector is functioning. So what the reality, if you like, the way where quantum mechanics is taking place here is in this configuration space. Okay, so you've got the one dimension of the two slits here, but then you have to introduce a coordinate for the detector, and that detector wave function either moves upwards or it moves downwards, depending on which slit the particle goes through. And so as it does so, as the y coordinate goes up here of the detector, it means that there's a channel created in the configuration space which is raised up relative to the channel in the configuration space for the particle which is passing through the lower slit. Okay, so the reason interference disappears is just because the waves, one would tend to think just in real space, are still crossing, but the reality of quantum mechanics is in configuration space, and there, if you like, the trajectories from the two slits are now not meeting each other, so they're not interfering, separated. And so there, Richard Feynman, is how you do it with hidden variables.
Are we assuming that the detector blocks one of these bits as it detects?
No, it's just sitting in the middle, looking to see which one it goes through. And as it sees which one it goes through, it changes its state.
But wouldn't it have to interact with the photon in some way, in some sense?
Yes, in an unspecified way.
Okay.
Yes. I'm not saying how that happens. Or what happens is the detector goes to an orthogonal state. Okay. And that's enough. That's all you need. But the key point here is that it's a configuration space motion, and Feynman probably is right. There's probably no way to do this if you just stick to 3 dimensions of space and time and hidden variables. Oh yeah, okay. I should have said all that when that slide was on the screen, so I'll just skip over that one. So, introducing a measuring device increases the number of dimensions of the system's configuration space that we're considering, and a well-functioning measuring device will separate the evolution in the configuration space into separate channels, non-overlapping. There's no wave packet collapse required because the system's got to go into one channel, it's following a path, it's going into one, and so we don't need wave packet collapse. We can define something called the conditional wave function of the particle, which is that Yeah, sorry, this is an error here. It should be psi of x and y. Yeah, the configuration space. No, it shouldn't. Psi of x is the configuration space wave function when you actually specify a particular value for the detector coordinates. Okay, so it just becomes then a function of x. If you do have an irreversible functioning of the apparatus, then you can destroy the coherence of these two channels, and then you have something which we call an effective wave function. So for all practical purposes, effectively, but never actually, there is a collapse of the wave function. But in Bohm's theory, you never have to collapse.
I'll ask a question. Would it be legitimate in this way of looking at it? In configuration space, would that imply that each particle is in a sense travelling in its own three-dimensional space?
Yes.
And the question is, how these spaces now interact rather than the particles?
Well, I mean, certainly in Bohm's theory, each particle is travelling in its own space. And if you define this conditional wave function, each particle would have its own quantum potential in that space, which is causing it to move in a particular way. But you can't calculate that if you just stay in real space. You have to go to this configuration space, which is where the wave lives and where it interacts. So a very important point, I think, which is lost, I think, in initial introductory texts, is that quantum mechanics can't be formulated or understood solely in everyday space, which I think is a difference. I'll say that now, actually. Yeah. So how does this kind of thing, how could this fit with the deterministic universe? And of course, very tantalizingly, when I see your pictures of the two slit experiment, I think, well, can you calculate trajectories? I'd like to talk to you about that, how that would work out. Another problem, I think, possibly for the deterministic universe is that we go to many particle quantum mechanics. It's really all been single particle quantum mechanics. And the single particle universe is a very boring place, so you need at least two to make anything interesting. And really, I think many particle quantum mechanics is the essence of quantum mechanics. Right? It really there's no classical analogue. It's not like waves going through a slit or anything like that. So the two particle stuff, I think, is more instructive about the nature of quantum mechanics. And so just recently, as a theoretical quantum optician at Portsmouth, who reminded me about this Honru-Mandel experiment, which is actually quite an old experiment. And I did do some similar calculations on the Horn-Shimony-Zeilinger experiment, which is a very similar sort of experiment. But this experiment, for those not familiar with it, is that you have two photons. One comes from here to a beam splitter, and the other one comes from here to a beam splitter. And the curious thing is that even though when you send one photon in, it's either reflected or transmitted with a 50-50 chance, when you send two, they both come out the same way if they're bosons, right? So never do you get coincidence detections in C2 and C1. And this is a pure quantum mechanical effect. So how do we understand this in the Bohm theory? Well, again, we have to go to configuration space, and we form this entangled wave function. In fact, it's a function which is either symmetric or anti-symmetric, depending on whether we're using bosons or fermions. And the calculation I've done is for massive particles. And we can try to understand how this happens. And we can visualize this also in a configuration space. Okay, so just go back a minute. How do I go back? I won't go back. Yeah, so this is a configuration space representation of those, because we've got here particle 2 coming from the upper packet, while particle 1 is coming from the lower packet, so like that. And the symmetric case in green is that particle 1 is coming from the upper packet, while particle 2 is coming from the lower packet. So we have to have this symmetry in the configuration space. And then we say, what happens when we let this go? So these wave packets are now approaching the beam splitter. They're symmetric in the configuration space. And how does it work out that that if we do the calculation, we find this is the way things evolve. So as you will have seen, the packets approach the center. There's an interference in the center in the configuration space as the packets overlap, and then they separate. They separate along the diagonals. So you'll see there's a probability of finding a particle here, the two particles here, where we have both of them in the negative, something is below the beam splitter, and there's a probability for finding them above the beam splitter. And it's really quite straightforward to think about how things work in the Bohm theory, especially if you've been doing it for a long time, because the trajectories just follow the flow of the probability densities. Okay, and so how do they look? Well, this is how they look. So this is trying to show an x1, x2, so dimension particle 1, particle 2, and this is time up here. So as the wave packets approach the beam splitter, which is in this region, particles move in, but then they interact and move apart. Can't see it so well in this picture, so I've also plotted an x1, x2 picture here, where you'll see that the packets come in. They can't cross this line across the center here, so the trajectories have to turn around and go either up here or down here, and similarly from the other side. And that's how it looks in the configuration space. You'll see that they don't cross in the configuration space. They're a bit dense, so it's hard to see that. But they can't cross in the configuration space. But if we project this configuration space onto the real space axes, so we have x1t and x2t, these are the individual, so these are the trajectories for particle 1. If you just were to look at particle 1, that's what you see, no interference, and it goes either way. And similarly for particle 2. Okay, that's particle goes either way. So it's only when you look in the configuration space that you can see this purely quantum mechanical effect in which the particles are tied together when they leave the beam splitter. Okay, they have to come out the same way, and obviously there's a non-local connection between them. It's local in the configuration space. The wave just evolves locally, but if you project that out into the real space, then you see a non-local effect. And this is also one of the things I think that worries me about. Have we got time for the fermions? Quickly. Okay, so that's how the fermions work. Okay, so it's the same story, but instead of coming out on the same side, if you have fermion particles, the antisymmetric wave function, they have to come out on opposite sides. And this is just what happens when you turn the handle on the Schrodinger equation and integrate the trajectories. And that's what they look like, in some ways, very similar. So this is just to compare the two. And this is also quite instructive in terms of how we understand the Bohm theory, because you can see that just changing the sign in the entangled wave function from plus to minus, you completely change the potential which exists in the configuration space, which the particles see and react to. So it tells you that the quantum potential isn't like a classical potential at all. It's not a function, a pre-assigned function of position at all. It's a function which is determined by this configuration space wave function, and that's what allows us to bring in all the non-locality. Okay, lesson 5. Configuration space trajectories are determined locally in configuration space, but they bunch in correlated particle interference fringes. In the far field, both positions and momenta are correlated. Everyday space-time trajectories can only be recovered by projection of the configuration space trajectories into everyday space. You cannot do the calculation in everyday space. The separate particles don't have their own Schrödinger equation. When I tried to produce separate particle Schrödinger equations, they were turning into horrible integral differential equations, and I thought, well, okay, I don't think I want to go down that route, because they would contain anyway the coordinates of the other particles. So you just cannot formulate it in everyday space. I've already talked about the conditional wave function, but that's the way of thinking about how the particle responds depending on the other. Okay, time for EPR or not?
Yeah.
Right, very quickly. Okay, well this, I'll just do this very quickly. This again is part of the infinite potential film, but this is the EPR setup where we're measuring spin on this side, we're measuring spin on this side. We're using the Bohm-Schiller-Tiontno theory. We're starting off with a spin zero entangled state. So Z is the vertical axis in these diagrams. And actually it's really a one-dimensional space model, because we're just using time to parameterize distance in the perpendicular direction. But as the process goes on, this state, the spins become correlated with the spatial wave functions. So there's a wave function which goes up and a wave function which goes down, state up and state down, and these are correlated with the outcomes plus and minus for the spins. And when you do this calculation, again this was done in the 80s, what you find is that what determines the outcome of these measurements when the magnets are aligned is just where the particles are in relation to each other in this vertical plane as they enter the magnets. Okay, so these can be separated from the Milky Way to Andromeda. It makes no difference, as we understand with non-locality. Actually, there's no dependence on distance. So this one could be on the Earth, this one could be somewhere in Andromeda. And so this is just doing the calculations, showing them in a visually attractive way, in which you could see that when one particle goes up, the other particle goes down. So we know that the outcome on one side of the experiment for one particle depends on where the other particle is, even though that one's on Andromeda. Right? If that particle were to be in a different place, you'd have a different outcome on the Earth. Totally mind-boggling. How can this possibly be? And that's what this theory tells us. But in a way, it's even worse than that, because not only does it depend on where that other particle is at its entrance slit, it also depends on whether you switch the magnet on or off. So you can affect what happens over on the Earth. I can't remember which way round it was now. Over on the Earth by many light years away. Switching off a magnet can actually change what happens to the So we switch the magnet off, and now we see that what should have been, this particle should have been, had this been on, this particle would become spin up because it's higher in its entrance plane than the one on that side. But in fact, when you switch this magnet off, you just really get local behavior here. And with that position, this one becomes a spin down particle. Okay, so how wonderful if we could actually use this for signaling, right? We just switch the magnet and this particle would go down. Of course, you don't know which way it was going to go in the first place, so you can't use it for signaling. But the theory says that that's, that is what's happening. There's an instantaneous non-local connection between these two. So this particle over here knows whether that magnet is on or off. Okay, so that's just repeating what I said about this changing its motion depending on whether that magnet is on or off. Okay, so I think what we can learn from this, and this is very nearly the end, the relationships governing space-time motions of objects are not determined solely by their positions in everyday space. Instead, individual motions are determined by the evolution of the configuration space wave function and principle of the whole universe. Okay, so it's not the case that only things which are near can interact. And so somehow this everyday notion that we've built up, which works really well in our everyday life, is actually misleading. That is not reality. And so then you have to have a theory which explains why it is that everything that we every day feel and operate with is the way it is. And I think that can be done in a quite straightforward way by showing how you can factor the configuration space wave functions into a wave function concerning a big lump, which would then behave classically. Okay, there have been a couple of papers on this actually. So this non-locality, I think, is it's. I think. Yeah, so what I was going to say is this non-locality, although it sort of coheres, has an analogy perhaps with DU, it is a very different kind of thing, although it wouldn't be foreign to DU to have non-locality because it has that already. But how those two things, if they have anything to do with each other, I'm not sure. So they're my main conclusions. Obviously, having mentioned the word instantaneous connection with so many relativists here, that's obviously going to raise some issues. But there's two ways out of this. One is to take the deterministic universe approach and say, no, there's an absolute frame. And that's the frame in which the connection is instantaneous. Bohm himself preferred this approach to say that there is actually an unobservable but nonetheless existent preferred frame. And there's no contradiction with relativity to assert that. I should say it was Lorentz's idea, I think, to do that. But also having said that, of course, it's a challenge to de Broglie-Bohm theorists to see if they can't create a relativistic version of the Bohm theory. And there are candidates out there, one of which I had produced with George Horton, but there are other ones produced by the likes of Goldstein and Timorka and other groups. So that was, I think that's my last slide, it should be, conclusions. So I hope I've given you some insight into the way the de Broglie-Bohm theory works and how it might be of some use in the deterministic universe.
Dynamic universe.
Oh, sorry, dynamic universe. Yes, it is also deterministic, I believe, isn't it? But it's referred to as a dynamic universe. Thank you, Barbara.
Thank you.
Thank you.
Any questions?
Yeah.
You have a question?
When you say particle trajectories, do you sort of mean an actual particle following a trajectory in real space, or are they always in configurations?
No, the particles themselves are always in real space, but their motions are controlled by the configuration space evolution.
Okay.
Particles, and if you like, the quantum potentials are also in real space.
Okay, so
But the wave function isn't.
the
The wave
particle,
functions, yeah.
if a particle goes through a two-slit experiment, it doesn't follow a straight trajectory. It wriggles
Yes,
as it goes through.
yes.
How does it exchange momentum with the environment if it does that?
Well, in the theory, it's acted on by the quantum
So
potential.
it is by the quantum potential.
Yeah.
Okay.
Sorry, I just have a question.
Yeah.
Thanks. Correct me if I'm completely wrong from the beginning, but I remember, like in classical physics, I believe when you have the Lagrangian formalism, and you have the configuration space, and there is the Legendre transform, I'm not sure how to mention that right, with which you can move to the phase space of the Hamiltonian mechanics. And so, to my understanding, one of the main reasons why such Legendre transformation is not possible in quantum physics is because there are no trajectories or no smooth differentiable functions and stuff like that. And this I find this quite interesting because at the same time in the more like the later version, especially of Heile's work, of phase-space formulation of quantum mechanics is very central to that, but it doesn't happen through the Legendre transformation. It happens through the Wigner transform, which is like a totally different animal from my understanding.
Yes. Yeah.
And I'm just wondering how all this stuff with the trajectories and all these like they just don't fit. Like somebody says that you can't have if you had trajectories in quantum world, then you could do the Legendre transform and go to the phase space. But it is possible to go to phase space formulation, but it doesn't happen that way. And all this stuff is just really confusing. So
Yeah.
you have
Well, okay, but I mean, this theory, as I've said in the summary, it's actually non-classical, and so it's not obvious that anything you can do in the classical formulation, you can also do in the de Broglie-Bohm approach, because this is a very specific approach in which position is given the central position. This is the key to it. So although one could make phase space diagrams and so on, they wouldn't be the fundamental ones, and they would be derivative, I think, on the calculations which you do in the configuration space and to get the motions in real space. So
does this follow from the special place of the expert representation theory?
yeah, I would guess that that's the case, but I couldn't say that I have actually worked that out and gone into that to find out why that would be the case. There are many differences with classical mechanics, and I think one of the problems that people who support Bohm face is always people think, well, you're just reinstating classical mechanics. But David Bohm himself would say, no, that was definitely not my intention. What I wanted to do with this theory was to put it in as close a form as possible to classical mechanics so that we could see clearly exactly what the differences were. So, it's not a classical theory which you can then incorporate all of the theoretical structures of classical theory, because it's not a classical theory.
Right.
Yeah, yeah. Thanks. It's a very interesting talk. Yeah. So I just wanted to ask. So in the last when you were doing the EPR, so that separation was also in configuration space, right? The bit.
Well, actually, those pictures were the trajectories in real space. Sorry if I didn't explain that properly.
No,
That's especially a representation of
No, the yeah. So the starting point of the electron for the spin up or the spin down, that separation that you showed was in configuration space, I guess.
Yes, essentially, yeah. So you'd have to think that the two particles, they're entrance slits, and when I drew them like that, that was effectively a configuration.
Okay.
Yeah.
And then you say that when I guess you said that for the Hongo-Mandel part. So when you projected to real space, there was this very complicated integral differential. But those could still be very interesting because that's kind of showing the entanglement or that's a quantification of
yes, indeed. Yeah, that's right.
Yeah, thanks for the interesting talk and illustrations. Just a big picture question for those of us from outside the field. Given the growing interest in entanglement, where does Bohm's interpretation stand? So, is there kind of movement towards his ideas? What's happening with the comparators who still think about collapse of wave function? What's the overall picture in the broader community?
Yeah,
I know here there are people interested in that there.
Yeah, I mean, I'm personally also a supporter of Bohr, actually.
Right.
Both are, in my view,
Right.
completely consistent approaches if you stick to them. They're perfectly consistent. But when I started doing these calculations, when I did those two slip trajectories, 1979, there was nothing. Well, there was a bit, but nothing. It wasn't. You could go to a conference on foundations of quantum mechanics. Nobody would mention Bohr. That changed for many reasons. John Bell was very strong supporter of Bohm, and in fact did a lot to publicise the views. Then there were some books on the subject, which contained a lot of this work. And gradually it's grown. How it stands now, I was interested to have a chat. Sorry, I've forgotten your name already. with Paul over lunch, and because he's been out of physics, came back into physics. He said when he came back in, he was totally surprised to find that the many worlds theory was in the ascendant. And everybody thought that was the theory. So, to answer your question, I think today it is very well accepted that there are several viable alternative interpretations of quantum theory. Today, Bohm's theory is counted as one of those. Many worlds, and so on.
Confirming. I just wanted to confirm upon this question here. There's a paper from Angel Sainz, which was published, I think, 15, 20 years ago, where he looked at the citations of David Bohm's original, and it was very flat until the end of the 20th century. And then in the last 20, 25 years, it's just been shut up, kind of blown out of all proportion. And I just got a message that Bohm's and Hiley's book has now 1,500 citations for the undivided universe.
Yeah.
So, there's more acceptance, I think, indeed.
Yeah, definitely. It's more acceptance.
Yes, thank you. It was really interesting talk, and you found those relations and similarities between DU and Bohm's theory. It was really interesting, but what I'm just wondering about the relation between this configuration space and real space in Bohm's theory. And it is an abstraction, you say, but that doesn't give me a clear picture what is going on there, and I was just thinking, and can you predict anything what is happening in the real space, or based on those what you can calculate in configuration space?
Well, yes, it's a short answer. All of the calculations that you would need to do using the Schrödinger approach to many particle quantum mechanics, you would have to do those calculations in a configuration space and many coordinates.
Yes, but can you then, you said it is deterministic, but can you then give a certain predictions that this will really happen, this option, not that
right,
one?
Okay. So, yeah, I guess I missed that bit out. Because although we have these definite particle trajectories, it's very much the case that you would say, if it were to be the case that the particle was here, and say the other particle was here, they would follow these trajectories.
Yes, but in principle you cannot say.
But we cannot.
Yeah. Yes.
Any attempt to say, well, let's make the particle start here, you would have to interact with the system, you totally change the wave function so that it became, something like a delta function here rather than a spread out wave. So you see, we can't control the hidden variables. I mean, Bohm in his 52 paper said, well, that was the situation. But it may be, that when we go to high energies or, that's basically what he said, when we go to higher energies, we might find, some different theories. It may be possible to change this theory so that there are predictable differences. But until that case, the Bohm supporters are quite happy to shelter under the umbrella that all of the predictions of Bohm's theory are the same as quantum mechanics.
Yes, thank you.
So I think I had 2 questions. The first one was, how does configuration space relate to the quantum phase space that Apple was looking at more recently? And the second one was the fact that you got position and momentum as almost classical type variables. Is that the consequence of not having quantum gravity? Like, if you had a deeper theory, would you then get a sort of quantum or non-faithful measurement of position and momentum?
Well, yeah. If we had a quantum theory of gravity, well, since we don't have one, I can say whatever I like. it could be possible. When the theory changes, it may be that these things would become distinguishable. Yeah. And sorry, I forgot your first.
So the first one was, I was wondering how the configuration space related to the quantum phase space that Basil was looking at in the past.
If Basil was here today, he would say, "Oh, there's no wave functions. There's no such thing as a wave function." And he would say, "There's only these algebras. We can get the quantum potential out of the algebra." So he was not, in his latter years, a fan of wave functions. So he wouldn't do. He wasn't. He in fact, I think this was always Bohm and Hiley's vision that, Basil, somewhat unkindly, used to refer to the 1952 theory as a Mickey Mouse theory, because it was cartoons, we could make cartoons of how things worked. But in ultimate reality, for them, I think, was in the implicate order and how we describe the process of becoming. And he found algebras, Bohm and Hiley found the structures of algebras much more amenable to thinking of the basic way the universe works in terms of processes and how you can get out of those basic processes described by algebras something which appears to be like a wave function, even though they don't exist with Basil.
Because there's the papers by Robert Callahan and Basil Hiley, which show that the same information is contained in Euclidean algebras as is contained in the wave functions.
Yes.
Yes, I see. So it's just 2 different pictures, but the idea is that the quantum phase space based on an algebra is going to be a more physically useful picture than the sort of than like it has more depth in it, whereas you're getting rid of lots of information if you're going to just the configuration of space with the wave function, or am I misunderstanding you guys?
I think we'll talk about it later.
Okay.
Go on,
Yeah.
Trevor.
Yeah. Right. Yeah. So I didn't follow Basil down that path. So.
Any other questions? Anybody?
I think one of the lessons that Basil sort of kicked into my head, I reduced there, was that if you do try to go down the path of making simplistic, three-dimensional models of each other, eventually those models would betray you. So you always caution against doing that, even though we live in such a world where we always caution us that the theory doesn't allow us to do that. I think that's the point. It's the theory doesn't allow us to do that. Whether we will be able to in the future, of course, is an open question. But he always said, look, just be careful, just don't, if you go down that path, eventually those models that you're trying to build will betray you and give you the wrong answer. Even though they're very pretty and we all love them, but so I think you have to do that, and I think we just have to take for granted, might not be the right word, we have to just take it, but we're not in a position to be able to build three-dimensional, four-dimensional models that will always give us the right answer.
Yeah, well, that's certainly that. Yeah, I would agree. Quantum mechanics is a multi-dimensional theory. However you want to cast it, you're not going to be able to describe it in the ordinary.
It's almost like each particle sits in its own space, and sometimes they come together, and other times they.
Yeah, I think for me, what is the insight of this is that our everyday three space that we're quite happy in isn't what it seems, right? Because we know that there are the relationships between objects aren't just determined by how near we are. They can be determined in a whole other way through configuration space. So I think our everyday world, just as, if you like, with relativity, we think there's an absolute space and time, and there may well be. But relativity shows us that isn't the case. So similarly with quantum mechanics, we quite happy in our everyday space, but the reality is something else.
Thank you very much. Thank you.